Good question to end on here, a little bit different. We've got the numbers from 1 to 20, the first 20 positive integers, and we're trying to write a list of n different numbers so that no two of them differ by 5. So for example, we couldn't have 1 and 6 in the same list, or 6 and 11, although we could have 1 and 11. We also couldn't have 11 and 16. We're trying to find the largest amount of numbers that we can have such that this is possible. So if we write down some of the problematic numbers, 1, 6, 11, and 16, so we can actually have 1 and 11, that would be okay, or we could have 6 and 16, or we could have 1 and 16, that would be right. So I could pick 2 from this list, but I definitely couldn't pick 3 or 4. And the same is going to go for other lists. So 2, 7, 12, and 17. I'll be able to pick just 2 from this list. Let's keep going. 3, 8, 13, and 18. Then 4, 9, 14, 19. And 5, 10, 15, 20. So as I've said before, we can take at most 2 numbers from this list. But in fact, we can take at most 2 numbers from each list. And that gives a suggested n, so max n, or I should probably say that n is going to be less than or equal to 10. There's no way that we could take 3. I hope I've justified that, because as soon as you take 3, one of them will necessarily differ by 5. Let's just see then if we can make a list. That's always a good shot at this sort of stage. So 1 and 11 would work if I just make sure that I make them differ by 10. 3 and 13. We don't have to go for the middle ones. We could go with 4 and 19. And we could go with, say, the second one and the last one. So that would work. Right. So now how many ways? Oh, sorry. So I should probably add at this point. So n equals 10 is the largest possible value. I didn't actually show earlier that it would work. I just showed that, in theory, that is the most it could be. And I've just gone ahead and found an example to show it is. But n equals 11 would fail because then I would need to have 3 from one of these lists, and they would necessarily, like a pair of them at least, would necessarily differ by 5. Okay, now it just comes down to finding, I say just comes down to finding how many different lists there are with this many numbers, all the possibilities. So it actually comes back to something that I said before. For this list over here, I said that there were 3 different options. 1 and 11 because they differ by 10, 6 and 16 because they differ by 10, and then 1 and 16 because they differ by 15. So for each mini list, there are 3 options. In the answers, they decide to go with A plus 5, A plus 10, and A plus 15 because all of these lie in this form. So I think it's quite a nice way of showing it. I got to admit, I didn't do that. I just said, oh, it's going to be 3. I didn't justify it any further than that. I felt like it was obvious enough. So we could pick A and A plus 10. We could pick A and A plus 15. Or we could pick A plus 5 and A plus 15. That's it. So 3 options per mini list. and there are 5 mini lists, then this is where the product rule of counting comes in. We're simply going to do 3 to the power of 5. Because say you had your first mini list and you picked it, then there's going to be 3 ways to pick the second mini list. But then for each one of those, there's going to be 3 ways to pick the third mini list and so on. So just like when you pick in, say, 4 t-shirts, normally I start drawing t-shirts at this point, but I'm just going to say 4 t-shirts and 3 pairs of shorts. See, for every t-shirt, you could pick 3 pairs of shorts. So it's going to be 3 plus 3 plus 3 plus 3, or 4 times 3. It's the same here. For every every like option we have for our mini list, there are then 3 options for the next mini list. And if you bring, say, 2 pairs of socks in, for every pair of socks, there's going to be 4 times 3 options for the t-shirts and shorts. So it's going to be 4 times 3 times 2 here. This is called the product rule of counting. So we get 3 to the power of 5. Now, 3 to the power of 4 is actually 9. It's 3 times 3, 9. Then times by 9 again, so 81. So, there's little shortcuts to working these things out. It's 81 times 3. There's going to be 243 possible lists. I really like this question. It's got a little bit of arrangements in it. It's got a bit of, deduction and arguing your solution. Hope you enjoyed it as well.